the Engine Performance Expo. Again, Lake Speed Jr.
Dyno MacAskill, Shaver Racing Engines.
You've seen us before. This time we're not talking about a dyno for a change.
No.
We're in the dyno room, but yeah, that's just because it was quiet, easy place to set up and talk.
Exactly.
We
feel comfortable in here, too.
We do feel comfortable. This is our zone. We're a safe place, happy place right here. So, what we're talking about today is an advanced technology feature called REM, or a super finishing process. Now, Don, tell everybody why you guys use it, because people think about you guys as race engine guys, but there's a lot more things you guys make here besides race engines.
Well, there are. You know, one of the biggest things that we make here for racing engines, besides lifters and a few other things, we make our own Shaver Westmark gear drive. We make all these parts here, and then after they're machined, which we do on a CNC machine in a gear hopper, that gear, we have to send them to a heat treater to be heat treated. We can't send them before that, or else we wouldn't be able to cut them. Right. But after they come back from the heat treat, we were one of the first people in Southern California that actually had a REM machine. And basically what a REM machine is, it's a big tumbling machine. It has different size media, or they look like little rocks, different size media in there, and the machine vibrates and it tumbles just like a regular rock tumbler machine would, except for it's made for automotive parts.
Right, like a rock tumbler, like people who had a kid had a little rock tumbler,
kind of the same thing.
Polish rocks.
It does the same thing. However, it's a slightly different process for when you're working with a metal part. Now, you can put a lot of different things in there. We use it mainly for our gear drives, but you can actually, our machine is big enough to put a crankshaft in, you know, springs, rear end gears are huge. People are finally realizing that the friction in the rear end gears is much less after you rem it. And that basically what it is it's polishing the material. And it's a two-process deal. So we'll get a gear back from the heat treater, and it'll be kind of ugly. It'll have like a satin finish on it because the heat treat process makes it look really ugly. Yeah. So they'll sandblast all the ugliness off of it and give it back to us, and we'll stick it on our REM machine. Now, what happens is it's a two-step process. As I said, there are two different chemicals that go into finishing a steel part. The first chemical is basically called a cutting solution. Okay. So that cutting solution, you put the parts in, you turn the machine on, and it shakes and jiggles and makes a lot of noise. And it starts feeding. There's an automatic machine that actually starts feeding the fluid in at a specific rate as the machine is tumbling. Now, the first solution that we use, and it goes in for about, I think, 160 minutes, is the first process, which is the cutting process. What the cutting process does is, with the media itself, is it takes all the high spots off. All the peaks. All the peaks off, and Lake's going to talk about the peaks here in a minute. But it takes all the high spots off of the metal, and it starts to smooth the process out, the finish out. It actually smooths it out. Now, I have two different gears here. This one just came out of the CNC machine, and this is one that's been red. Now, you can't really tell in the video, but this one actually looks a little shinier. The problem with this one is the finish on this is really horrible from the machining marks. We'll show that in a minute. This one here is a lot smoother. Again, you can't see it, but he's going to explain that in just a second. So after the first process is a cutting solution. If you were to take the gear out of the REM machine after the cutting solution, it's going to look kind of ugly too. It's going to look kind of dark, and it's going to have spots on it or whatever. But the finish will be a lot smoother. The second process is what makes the gear look really good and work really well when it comes in contact with other gears, such as the tooth of the gear coming in contact with the tooth of the crank gear. And the polishing solution goes in the second part of the REM procedure, along with a water flush. And again, the machine does all this automatically, so all we have to do is push a button and come back, you know, in 5 hours, and it's done. Yeah, part. So after that, another 160 minutes on our gears of the polishing solution, that's when it comes out looking super shiny, and the finish on the gear is incredible. The gear wear is literally 50% less after we started this REM procedure.
Well, that's so key, right? It's not about making a pretty part. I mean, we all like things that are pretty and shiny. We're all squirrels like that, you know. But the reality is, you're doing it to make the life of the gear longer.
Exactly. And the reason for that is if you had an unfinished gear against an unfinished gear, all the high spots that are on that gear they're gonna wear out really quickly. And sometimes it wears out so much that the gear will actually fail.
Right.
Since we've started this REM process, we have not had any gear failures.
And the technical term, right, from the tribology side, we call that bearing area.
Bearing area.
And so we can use this really handy device called a profilometer, and we can actually measure these, and we're going to show you right now what those parts look like. So when you take that profilometer and you set it on the unfinished gear, right, the as machined gear, and start measuring it, you're going to see all those peaks that are come from the tool, right? As that cutting tool is machining that part, it's got a tool path, and it's leaving these high spots. And then those high spots don't provide any bearing area.
None at all.
So now it's like doing push-ups on your fingertips versus your palms. You're not going to be able to do as many on your fingertips as you can your palms. So you want more bearing area. So then when you look at the rim polish piece, you can see that those big peaks are now smoothed out, more like rolling hills. And your RA, your roughness average, which anybody knows me knows that RA can lie to you, but in this case it's a pretty good example. Your RA goes from 20 on the unfinished piece to 5 on the finished piece. And your bearing area curve goes from looking like a straight line, 45-degree angle, to actually having some area. And in that bearing area, more bearing area means more load capacity, which means for you, longer engine part life.
In the same token,
or gear.
On the same token, it means less friction.
That's true too. So better lubrication, better longevity, more power, better durability, kind of all good things, which is why you guys have a REM tank back here, because that's the name of your game.
We couldn't live without it.
Yeah, for the engines you guys build and the stuff you do for people, you got to have power and durability.
Yeah.
The world today in racing engines and high performance engines isn't an either or. Oh, I got to trade off horsepower and durability. Yeah. No, the goal is I want more horsepower, more durability, and I have both, and you can achieve that in a lot of cases by using the correct parts, the correct processes. In the REM process, that's just one of those ways.
That's correct.
To get both.
Yep, it's actually helped us gain a lot of power in the probably the 10 years we've had the machine.
Like I said, all your valve springs you come now.
Correct.
That way. It's a way of almost stress relieving the parts.
It's also a stress reliever too. Like for example, valve springs. Most of the valve spring companies these days are actually remming their springs because it takes all the high spots of the manufacturing twerks out of the coil, and then there's less chances of breaking because of that.
Yeah, so hopefully you enjoyed this little view into the REM super finishing process, how really easy it is to do, and what benefits it can give to you. Thanks for watching.
See you guys.
Hi there, Engine Performance Expo viewers. Again, Lake Speed Jr. from Total Steel Piston Rings, and I'm here at a really cool place, SoCal Diesel, my good buddy Guy Tripp. Guy, you're the Duramax Diesel guy, right? You're a big power diesel guy. How much power are these diesels making these days?
Oh, Lake, it's incredible. We're into the 3,000 horsepower at the rear tire.
That's just mind-blowing.
It's nuts.
That's like Pro Mod power, right?
It really is. The Pro Mods are making a lot more horsepower than we are, but the cylinder pressure is about the same. So when you look at how much bang is pushing the piston down in the cylinder, we're right there with the Pro Mods.
Like torque. What kind of torque values are these engines producing these days?
Interesting that horsepower and torque are related by a formula. So it's
exactly.
torque times RPM divided by 5252. And because we're usually right around the 5,000 to 6,000 RPM mark, usually when you've got 3,000 horsepower, you usually have right around 6,000 foot-pounds of torque.
That's just mind-blowing. I said, that's the cylinder pressure. He said the bang is equivalent to what's happening in a Pro Mod.
Exactly. They're at 10,000 RPM plus. We're at 5,000 to 6,000 RPM. So the bang is the same. It's just their RPM, the rate that they apply that bang is much greater.
Okay. And you're doing that with a stock block.
We're doing that with a stock block. Yeah, we're just about right at the end of
mine's blown on that one. I was like, how is that possible?
Yeah, considering what the GM engineers had in mind for this motor, it is pretty phenomenal.
That's not your daily driver.
Right.
I mean, but you guys are drag racing it. You're sled pulling. I mean, what are the engines that you build? What are they being? What are doing with these engines?
We focus primarily on the racing industry.
Okay.
We do have some towing customers that are looking for heavy-duty parts.
Sure.
Obviously, that has to work within all the emissions regulations.
Sure.
But a stronger crankshaft, stronger pistons, stronger connecting rods doesn't do anything to violate emissions. So a lot of our towing customers will take advantage of what we've developed for the racing industry.
Okay. Awesome. So with the Duramax platform, talk about what you've had to do to be able to achieve those levels of power and durability. Because you got a NASCAR background just like me. It's one thing to go fast down the track once or make one hero dyno pull, but it's different to do it over and over and over again. So talk about that a little bit.
My feelings on that are, these parts are expensive and they should be built to last a long time. Obviously, we want to target the industry, the application,
right?
What the customer's end use is. If there's a guy that wants to run his vehicle like a top fuel team and rebuild the engine after every run, so be it.
Sure.
But let's face it, the majority of us don't have that kind of budget.
Exactly. Yeah.
So my theory, my philosophy on this is let's build good quality parts that people can race for many, many seasons over.
Okay. So I'm sure one of the early upgrades to this, I'm sure you called our buddies down the street ARP, right? That was probably step one.
Yeah.
In this process, right?
Yeah, absolutely. It's really been failure engineering, I think, is the best description. We make a little more power, this part fails. So we engineer that part. We seek out a colleague in the industry, another company that already makes good quality fasteners. Obviously, ARP comes to mind for. It's the first name on everybody's mind when you're looking at fasteners. And then, what becomes the next problem? And you just kind of go through, and as the power levels increase, you're always going to find that weak part.
Right.
So, for us, that's been the history of SoCal Diesel the last 15 years, is pushing it to the next level. And when we find something that doesn't hold up to that level, we re-engineer the part and move forward.
Get your solution to find that next weak link in the chain. All right, so past head studs and things like that, fasteners, what was the next kind of thing you came across in trying to achieve these power levels? Because I see a bunch of crankshafts here, and I'm sure there's a story behind all this.
Right. Yeah. Yeah, absolutely. So obviously fasteners, pistons, rods, all of those things we needed to take a look at. So we started by redesigning the piston bowls.
Okay.
And looking to get those to live under extreme circumstances. Ceramic coating a thermal barrier on the top of the piston to prevent the piston from absorbing all that heat.
Right.
And getting past its yield strength and turning into a molten pile of metal.
Yeah, it's never really fun.
And then the crankshaft came shortly after that. So this has been an ongoing development process for the last, again, 15 years that I've been involved in Duramax racing.
So I see a two-piece crankshaft, and of course that's never a good thing. You finally found that next biggest link, which apparently is right there between the rod and the main journal. So talk about what you kind of learned here and how you went about solving it, because when you were kind of giving me some background earlier, it was just a textbook of, how you do failure analysis and overcoming those problems. So I would love for you to share with the audience kind of what process you guys went through to get the power levels and durability you're at today with this little evolution here.
Yeah, well, so right here is a classic two-piece version of the Duramax crankshaft. This is something that we encountered back in 06, 07, and it's what gave birth to our billet crankshaft.
Got it.
So we looked at, we're breaking crankshafts, so what's the next logical step? Well, we need a better crankshaft, better material. We need to add material in the areas that are breaking, where it happens to be weak. And so we released the billet Duramax crankshaft in 2007, which was a very successful part for us. It solved basically all the problems.
Right, yeah.
All the problems.
Better material where it needs to be to basically be able to support the load. But then you said, so not too long after that, there were some other things that came along that kind of built off of what you learned making that crankshaft, especially with the rods.
Yeah, sure. Not everybody can afford, a very expensive crankshaft, billet crankshaft like this. So we were looking at ways that we could still come back to the factory crankshaft and maybe solve those issues for maybe guys that aren't all-out racers but are still having problems with the broken crankshaft.
Sure.
So we looked at a number of different ways. to kind of solve that. Obviously, you want to identify what the problem is, not just build a bigger part, but maybe we can solve the problem on why, you know, that's happening. One of the things we went to is obviously a better harmonic damper. The stock damper is built around certain power levels, certain RPMs, certain frequencies. So we reached out to our good friends at ATI and worked very closely with them on the design of the dampener.
So you changed the dampener completely?
Completely. Yeah, absolutely completely. So right now we'll use the stock dampener for a doorstop. It works really good for that.
Okay, it's functional for that, but otherwise you call ATI, JC, those guys hook you up with the correct dampener. Now, you were talking a little bit about one of the reasons for this issue is the fact that obviously you get all this weight on the dampener in the front, and you got this flywheel in the back, and it's pretty easy now as this thing starts to do this, that weak spot tends to be kind of there in the middle. Yeah, absolutely. So this is an externally balanced motor, which means there's not enough mass, there's not enough room inside the crankcase to put a big enough counterweight to counteract the weight of the rods and pistons and rings and all that assembly. So GM engineers added weight to the harmonic dampener, and they've added weight to the flex plate, which is not uncommon for 54 Chevrolet, externally balanced motors all over the place. Oh, exactly, yeah.
The problem becomes when you're having crankshaft breakage issues, now you maybe want to look at the twist and rebound. So every firing pulse we have, we're pushing on this crankshaft and we're trying to get it to rotate. Well, we push on that with a whole lot of cylinder pressure. That crankshaft is actually going to twist, and then as the cylinder pressure decreases, it's going to rebound. Yeah. So essentially, we think of this crankshaft as this big chunk of metal, but in reality, when it's in the motor running, it's like the motor is taking that piece of metal and going and trying to break it in half.
Right.
It's in a twisting and rebound motion. So it kind of makes sense that if you've got a whole lot of weight hanging out on the nose of the crankshaft and a whole lot of weight in the back of the crankshaft, and we're pushing on it with various cylinders, that twist and rebound is going to be accelerated because you have that weight again that has to kind of follow what the crankshaft.
It's got inertia.
So the thought was, let's eliminate that weight. You know, nothing new in the automotive industry, maybe new to the Duramax engine, but nothing new to the automotive industry. Let's internally balance the crankshaft. Let's move all that weight inside. And the way we do that is we drill holes in the counterweight and we insert heavy metal.
Got it.
It's a tungsten alloy that's about 1.7 times the density of steel.
Right.
It did take quite a lot. We ended up with about 5.5-inch diameter slugs in the first two counterweights.
Okay.
And in the rear two, which was quite a lot. I'd never seen a crankshaft with that much Mallory in it, but it certainly helped.
Okay.
It certainly helped. It didn't solve the problem completely, but what it did is it extended the cycle life of the crankshaft.
So for your street type of guys who aren't all out race or they're lower budget race guys, that gave them an option between this and that.
Certainly.
Okay. And then you were talking earlier too about what you started to learn about the rods and the width of the rods and how you were able to, you know, that overlap make that crank stronger. So talk about that a little bit.
So the number one thing that you look at on the crankshaft when you're having these type of breakage problems is something that's called crank pin overlap.
Okay.
And that's the overlap between the crankshaft rod journal and the main journal. Basically this cross-sectional area right in here.
Yep. The meat in between.
The meat in between, right? And so that's the area, as you can see on this one, it broke right in that area. So the thought was, you know, how can we add material to that area to make it stronger? Obviously, we can't lengthen the motor. Nope. We're stuck with a stock block. That's kind of where we're at. And so one of the things that we looked at was the connecting rod. Now, the interesting thing about the Duramax connecting rod is that the rod bearing ends here, but yet we have another 1/8 of an inch material on the side of the rod that really isn't being used for anything. So my thought was, why not get rid of that?
Yeah, reduce it down, narrow the rod up.
Narrow the rod by 1/8 of an inch. Now remember, we haven't lost any bearing surface.
Yeah, you didn't narrow the bearing, you just narrowed the rod.
Right.
So that gave you the additional clearance, essentially, to thicken up that cross-sectional area to give you some meat back to increase the strength.
Exactly right. So by removing that 1/8 of an inch from each connecting rod, we were able to narrow up this rod journal 1/8 of an inch on either side, which increased this cross-sectional area by about 7%, which is absolutely huge.
Oh, that's a huge move. Yeah, exactly. Now, you were saying earlier, too, that not long after you guys came out with this, GM redesigned the stock crankshaft And there's a pretty good story about this. I'll let Guy tell this story because it's quite fun.
Yeah, we had the generation engines LB7 and LOY, which basically represented model year 2001 through 2005.
Right.
In 2006, they came out with the LBZ engine.
Okay.
And one of the biggest things we noticed right away on the LBZ engine is that it had a piston that had a bronze bushing in it.
Okay, yeah.
Right? It's pretty cool. We're looking at that going, wow, bronze bushing in the piston. That's got to be good for something.
So the previous piston did not have a bronze bushing.
Correct. Here's the previous piston on this side. No bronze bushing.
No bushing. Now you go to this bronze bushing. I mean, we're upgrading. We're going big time now.
It's a beautiful looking piston. You know, it had coated skirts.
Yeah.
And everything about it looked really nice. Unfortunately, and there's always a big if, right?
Mm-hmm.
Unfortunately, to add this bronze bushing in,
Mm-hmm.
we had to increase the material on the piston here, right? We couldn't just add a bronze bushing, bore this larger, and put a bushing in. That would make this too thin.
Right.
So fundamentally what they did is they had to move the bottom of the piston down to make room for this bushing.
Mm-hmm.
In and of itself, not too bad.
If you have room.
Right? We made the piston a little heavier. Might be good, might be bad. Let's play it out.
Mm-hmm.
What we learned was when this piston was at bottom dead center, on the early engines, you had about 45, 50 thousandths of clearance between the piston and the counterweight at bottom center.
40 to 50.
40 to 50. Point
Okay.
040, point, not much.
Yeah, my iPhilometer's already kind of looking at these two saying, yeah, that's about that or more higher.
Right. So when they put this larger piston in, you know, at some point they found when this piston was at bottom center, it was going to contact the crankshaft.
Yeah.
So what they had to do was reduce the diameter of the crankshaft, right? Reduce the diameter of the counterweight on the crankshaft.
So they shrunk the counterweights.
Right. So now we've kind of gone what I would consider to be in a backwards direction. We've added more weight internally
Mm-hmm.
to the rotating and reciprocating areas.
Right.
And we've taken weight or counterweight mass away from the crank.
So you're making it go to the ends
Right.
to make up.
So now the motor's out of balance. We've got to bring that balance back in. GM added more weight to the counterweight, more weight to the flywheel,
Mm-hmm.
exaggerating our inertia problems with twist and rebound.
Right.
And so how do we know that maybe that wasn't the best way to go? You know, maybe this was an accounting situation. Maybe this piston was way more cheaper than that one. Who knows why they did it? But what we do know is that crankshaft failures went up drastically, even in stock trucks.
Yeah.
And so even if we take that aside and we look at, well, what was the next generation when GM moved away from the LBZ and LMM engine into the LML?
Mm-hmm.
What did they do there? Well, they no longer use the piston with the bronze bushing in it.
Ah, surprise, surprise.
They shortened the piston back up on the bottom. They added the mass back to the counterweight, lightened everything up, lightened up the flywheel, lightened up the dampener. I'm not a smart guy, but I'm smart enough to pick up on that.
Yeah. You can read the tea leaves on that one.
Exactly.
Okay, cool. So then, because one of the things you noticed, we mentioned before, is that from here to there, they increased the diameter of the rod journal. So when they were trying to make it stronger a little bit by moving that overlap, by making it larger. So now your new blocks are all made for that larger diameter. So obviously this won't fit in a block made for that, right?
Well, new crankshafts, right? So the new generation engine was the L5P, and obviously GM is looking for a way to increase the strength of the crankshaft, just like we are. And so they went back and looked at that crank pin overlap. I fully expected them to come out with an NR version, a narrow rod version, because we had this version of our crank on the market. But instead they went to a larger diameter. So they increased the diameter of the rod journal, which effectively increased this crank pin overlap, right?
Yeah, so it's supposed to have a mate like this,
right?
It goes like that.
Exactly.
Yep.
Now that didn't bode well for the regular connecting rod, because with the package in the bottom end, this type of straight cap rod would no longer fit in the block.
Okay.
So they went to an angle capped rod version, which is much like you find in the Cummins motors.
Exactly, yes.
Interestingly enough, my CAD analysis of our billet crank and our crank pin overlap cross-sectional area versus the L5P, it is so close. I mean, it comes up to within the thousandths. It's really phenomenal that, you know, two separate mines, two separate companies on opposite sides of the country ended up at the exact same crank pin overlap, and in different ways.
Right.
One with the narrow rod and one with the larger rod journal.
Yeah, trying to get the same idea though, getting the meat back where it needs to be to make it strong. They both got there. And then based on this size journal, you came out with a newer crankshaft, a billet version essentially of this. Is that correct?
Yeah, that's correct. So obviously, as our customers push the envelope with their newer trucks, they're going to need a billet version of the L5P crankshaft.
Yeah, better material than what's there. And
better material. Obviously, the crank trigger has been moved from the front of the crank to the rear. So essentially, we made a billet crankshaft that would fit into the L5P platform.
And this is more internally balanced than that, essentially.
Correct. With we did that in two versions. We made two versions of the L5P crankshaft. One is with the larger rod journal for this crank pin overlap. But what we did as well is it's not only the larger rod journal, but we also narrowed that one up. So in effect, we added another 7%.
You doubled it up. There you go.
Yeah. We double dipped it.
It's super strong.
Super strong.
I like it.
Really good for our sled pulling customers. It's a super strong crankshaft. It's really heavy internally. And that inertia, I think, is going to help the sled pulling community. Drag racers may choose to go back to the earlier journal, so an L5P crankshaft with the LB7 rod journal.
Talk about that, the difference between drag racing and sled pulling. To the naked eye, I guess you'd say that, hey, here's a truck, it's a diesel, and you're going from here to there. First guy gets there first wins.
Sure.
How is that different?
Well, everything we do here is application based. So obviously the camshaft, the pistons, the engine you build for a tow vehicle is not going to be the same as a race vehicle.
Sure.
And then once we get into the racing community, you need to look at the application of sled pulling versus drag racing.
Okay.
So in drag racing, everybody's really familiar with that. We accelerate from 1 RPM to red line, we shift. RPM drops down, we accelerate through the gears all the way back. And the loads we have on the vehicle are, weight of the vehicle, aerodynamic drag, and so on. Sled pulling is a different deal. They're traveling at maybe 30 to 40 miles an hour, so air drag isn't really a big problem.
Yeah, probably not.
They do have this giant trailer that they're trying to pull down the track, which represents a lot of drag. And then, of course, you get to the end of the track and the pan drops, and that represents even more load and even more drag. And so perhaps maybe having a little more inertia, a little more rotating inertia in a heavier crankshaft or flywheel assembly may add to that as the truck gets to the end of the track, the pan drops, having something with a little more stored energy may just get you that extra couple of feet. So again, you got to look at the applications and what the parts are designed for.
Well, that's really cool. So what other kind of things, I mean, it sounds like you've spent a long time really working through the science, like I said, the limits of these engines, and have found some little areas for opportunity, fine-tuning, especially to the application, the needs of the application. For somebody that's new to diesel, new to Duramax, what kind of advice would you give them about, hey, here's kind of the do's and don'ts of getting into the Duramax?
Oh gosh, that's a really good question. Do's and don'ts of getting into the Duramax. First, I think it's a great platform. Duramax engine was a clean sheet of paper. For me, it was the first small pickup diesel engine that had a larger bore than it did a stroke.
Okay.
It was the first engine when it came out in 2001 that had 4 valves per cylinder. Okay. And me being a cylinder head guy. There. So 4 valves per cylinder. Well, what's the difference between 2 valves and 4 valves? Well, 4 valve per cylinder head, we can get more air into the motor at a higher airspeed, right? We've got more velocity through smaller ports. But with 2 ports instead of 1, we have the opportunity to get the air in quicker. Means throttle response is better. And then Bosch common rail injection, that was another revolutionary thing that came out with the Duramax. It really caught Ford and Cummins kind of flat-footed on that.
So they were the first one to have the high-pressure common rail.
Yeah,
absolutely.
And
that is huge. That's a game changer, right?
It was a game changer both from power and emissions, because atomizing that fuel into much finer aerosol, much finer mist, made it burn quicker, made it burn more efficiently, and that translated into more power and lower emissions.
Exactly. If you can't burn it, you can't make power with it.
And you almost can't find a late model diesel anymore that isn't high pressure common rail injected.
Just for those who don't know, what's the kind of the fuel pressure difference between, say, a non-high pressure common rail and what a high pressure common rail fuel pressure actually is?
Early injection pressure may have been at wide open throttle 5,000 to 6,000 psi max. Okay. In the common rail system, we are idling at 5,000 to 6,000. Originally, they started out at about 23,000 psi maximum at wide open throttle, and since then they pushed it. Now we're up over 30.
over 30,000 psi. So almost a six-fold increase.
Isn't that phenomenal to think about? 30,000 psi of fuel pressure.
It really is. Now, am I right in understanding that the injectors also changed and they went to multi-injection for one cycle, as opposed to having just one big squirt? There's like a whole bunch of little ones.
Well, yeah, what they did is they introduced pilot injection.
Okay.
And so the pilot injection was kind of a pre-injection to kind of get the flame started. And then once they got a good flame kernel going, then they can bring in the
throw more fuel to it. Right.
And then they came in with some post-injection. A lot of that was, all aimed at emissions.
Oh, yeah. Post-injection is totally emissions-based, right? Yeah, regenerating DPS and all that kind of stuff. I hate those. Man, it's not we hate those things, but it's not fun racing stuff, right?
It's not fun racing stuff.
Yeah, it's not big horsepower stuff, you know. Yeah. So I'm sure. So the ability to put more fuel, burn more fuel per cycle was a big part of being able to achieve these 6,000 foot-pound numbers.
Absolutely, I'm 100% grateful for the emissions breakthroughs, because a lot of the emissions breakthroughs give us higher fuel pressure, more fuel delivery.
Right.
Faster ECM, faster injectors.
Oh yeah.
So all the stuff, efficiency is great no matter where you apply it.
Exactly.
An efficient emission motor, an efficient racing motor, it's all good.
I remember going to one of the SAE conferences one year, and I sat in on some conferences and classes that were all about fuel economy, and they're like, "Why is a guy from a NASCAR team sitting here listening to EPA fuel economy things?" I'm like, "Because that's efficiency. What you call fuel economy, we call horsepower."
Yeah.
So I want to figure out whatever little tricks you guys may have up your sleeves that we might be able to apply to a race engine but make more power. I'm all about it. That
was huge for us when I was involved in NASCAR research and development, brake-specific fuel consumption. So you could have two motors that made 700 horsepower, but one did it with a lower brake-specific fuel consumption, meaning it used less fuel to make the same power, right? Well, what does that mean to a NASCAR guy? That means 1, 2, 3, 5 extra laps on a tank of fuel, and that's huge. That's huge.
Oh, that's how you win Michigan. That's how you win Fontana. There's a whole bunch of racetracks. You go to that racetrack knowing it's going to be a fuel economy race more times than not.
Yeah.
And what can I do? What kind of tune-up? What can I do for gear ratio? All those things. You go into it. Hey, if I can get a little bit, I actually have a whole lot.
Yeah.
Because it compounds like every pit stop. You get a little bit further, play that game. It's always kind of fun.
And the interesting thing about that is, and I think back to this, that if you and I were having this conversation, 15 years ago, and I was telling you that we have these, 420 inch, 427 cubic inch.
427 diesel?
Diesels making 3,000 horsepower at the rear tire, you'd have chalked it up to beer and bench racing.
Oh, exactly. It's like, oh, yeah. I call it vast that big.
Yeah, exactly. But yeah, here we are. Yeah. So the diesel world for me has just been absolutely phenomenal in what we've been able to achieve over these past 15 years.
That's awesome. So, Guy, if somebody has questions about this, wanted to contact you, what's the best way for them to reach out to SoCal Diesel?
They can hit us on our website, www.socaldiesel.com, our web store, shop.socaldiesel.com, and, of course, the phone numbers. Give us a call. We've got staff standing by. My staff loves to talk diesels, and they're all racers. They're not just warehouse guys that are shoving parts from one side of the counter to the other. These guys will be happy to build a motor from you from start to scratch, walk you through it all the way through, and make sure you have the best parts for your application.
That's awesome. Guy, thank you so much for your time. We really appreciate it. Hope you guys enjoyed this segment. Thanks for watching.
Junior at Kiebler, myself, Joe Castello. The diesel market, we're just scratching the surface of what is to come, and that's got to be exciting for you guys.
I mean, when he's talking about making pro mod level cylinder pressures, I mean, no wonder the crankshafts are breaking. I mean, that's insane. Out of the diesel. Yes. And the thing is, so obviously they're drag racing them. They're doing the pulling truck, and the fact that I said on the pulling side was actually more difficult than the drag racing side, because that load continues to increase the further you go down the track. And what a unique thing that is in an environment. And so it was kind of cool to spend this time with Guy and to understand that. But like Ed knows, I mean, this diesel thing isn't just SoCal Diesel doing that. I mean, it's everywhere.
Yeah. I'm just amazed. I think I heard him say 3,000 horsepower, 6,000 foot-pounds.
6,000
foot-pounds of torque. That's incredible. incredible.
That like I said, that's got to be like pro mod-ish, top fuel-ish level. I mean, that's why he's got Sonny Bryant cranks in the thing.
And I know anecdotally from doing street drags at Homestead Miami Speedway, these giant diesel trucks will come out there and rattle up to the starting line and then blast down the track and blow everybody away, and then right out the gate. It's pretty amazing just to see how it has evolved, and high performance 4-wheel drive trucks. Who would have thunk it like 20 years ago? And yet here we are.
In some ways, they're going back to what Roy said. You fix what breaks.
Mm-hmm.
That's what he did, man. Essentially, that's what they did. So we started with this engine, the Duramax, and we're making more power because we're doing this and doing that. And you just fix what breaks.
And improve it and make it better.
Yeah, keep going.
I'm amazed at these guys that are in this diesel market. They're pulling so much horsepower and so much torque, but the learning curve on this stuff. These guys are starting, and just like you guys said, they're breaking things, and so they have to learn on the fly. I mean, they've got to get this thing fixed and solved, and it just amazes me. It kind of harkens back, honestly, to the old Top Fuel days,
right?
When guys were trying to go faster and blowing stuff up, and these guys are kind of the same way. It's kind of School of Hard Knocks.
Absolutely.
So there's no roadmap for this.
No, there's no roadmap.
People hadn't been down that path.
Exactly.
I mean, they've been down similar paths, but not that path. And they've got to figure it out.
Just to point out, though, the Top Fuel guys are still blowing things up.
Yeah, well, that's true. That's true.
They're still blowing
Thank God they do, too.
Yes,
it does make it spectacular and fun.
Everybody out there, now's your time for Q&A. We got a couple of minutes with Ed Kiebler from Rottler, and of course Lake, a wealth of information unto himself. And Lake, while we're queuing up questions, if anybody out there in the audience happens to have them, just put them into the chat section and we'll hit these guys with it. That's the whole idea of having a live conference.
Right, exactly.
So if somebody has a question, they can ask. But before we get to that, I just want to commend you. You've been, like, these videos didn't just happen. You went out and you got the content and you made the content and for us to all enjoy and learn from. So hats off to you. It's been amazing to watch.
It's been a blessing to me. Yeah. I mean, to be able to spend time with the who's who of the industry and be invited in their shop. And of course, what you see in the video is what they said on camera. You're usually there for hours more than that, and there's other things you wish I wish you'd said that when we were on camera.
Sure.
You just learn so much. I mean, it's amazing. You learn that you don't know anything. What you learn. It's like, wow, there's so much to be known. You don't know anything. That the more you learn, you just feel dumber and dumber all the time.
Yep. Well, and behind the scenes here, like after we finish these bits, Randy was just walking out a few minutes ago, and that's it. We're just scratching the surface. To be a professional in any industry means that you've gone through thousands of hours, you made a million mistakes, and to be able to share all that knowledge in 1 day or 2 days, it's not possible. Nope. And so that's why people are going to go back, hopefully watch more, make some phone calls, reach out to you guys, reach out to anybody involved, and just try to increase the knowledge base and ask some questions, which you can do right now, and if not now, later. And I just want to tease again, we're going to end the day with a round table. John Causey, Warren Johnson, Roy Johnson, and Scooter Brothers, and me. Wow. I'm going to sit there and just
Scooter's in the house. Yeah,
right,
exactly.
So that's how we're going to end off day one here of Engine Performance Expo. Now there was a comment a little bit earlier. It's right here. Someone posted like, "Hey, try this, household product as a way to lubricate when you're cutting," and it just triggered me a little bit. Ed, talk a little bit about that, like some of the home remedies when machining as opposed to doing it what I would call like the right way.
Right. Well, there's a bunch of that home remedy stuff, and I've seen guys use, and you being a tribologist, I got that out without tripping over it. You understand it better than I do, but I have guys using Pledge and soap and WD-40 and all these different things, and it may work in one instance, but then again it may not, and it's all about the surface speeds, the RPMs, the surface feet per minute, all of that sort of stuff matters.
Well, the thing that Andy was really mentioning is that materials have changed so much, and that's the biggest thing, right? Is that the material you're cutting, the coating or the material you're using to cut it with, I mean, that's chemistry.
Right.
This is straight up chemistry, and that's where, there's some things that may work here and there, but you have to understand, well, why does it work? I mean, if I'm using this, it's kind of like the old we were saying before, at the Trackside Tech Talks, there's a reason why people could get away, and it worked really, not just get away with, that it actually worked. It worked way back in the day, putting automatic transmission fluid on cylinder walls to break in chrome rings.
Guilty.
I mean, there's a reason why it worked.
Yeah.
Chemistry-wise, I understand that chemistry. But when you aren't using a chrome ring, when you're not using the old Type F transmission fluid, guess what? You've changed the chemistry, you're going to change the outcome. So if we can understand the why behind the what, then that's really important. Just knowing the what, that can be dangerous, like you said, because it can be misapplied. So, and then that's the whole thing, is you don't want people to go down the wrong road. I mean, that's the biggest thing. It's you've got a lot of money and time, especially today with part supply being the way it is. If you may only have the one bullet, so you better not mess it up. So relying on just conventional wisdom sometimes isn't what you need. Again, that's kind of the ethos of having the Engine Performance Expo, is to provide a platform for people can go and say, well, you know what? Let me think about it. I mean, just last night at dinner, we talked and quizzed John Causey for 30, 45 minutes about, oil pumps and bearing clearances on the aluminum rod and all that, because I don't have experience using aluminum rods on a big engine like that. So where am I supposed to be? Well, John's got tons of experience on it. Ask John. So you want to use this network of resources to be able to bring things together so that when you got the one bullet, you don't miss your shot.
Right. And all of these guys here, Scooter and Warren and John and everyone, they've done it, and they've learned from the school of hard knocks and hard work and perseverance and all the, and what's so cool about this is they're willing to tell everybody else why it didn't work and why this does work. And if I can encourage anybody, or any little thing you take out of this, it's to listen to these guys. They've been there and done that. Now, they'll all tell you they're still learning. I mean, Roy was out there and talking about computers, and he's talking about that. I learn every day. Every time I go into a shop with you to shoot a video or something, I learn something.
Oh, yeah. Every time I do.
I've been at this for 48 years now. So I think if you quit learning, you just stall out.
Well, it's kind of like Roy said. Every day you can get a little bit better.
Right.
So if every day you're making little changes, incremental, guess what? 5 years from now, you're way down the road, which means now my environment is totally different there. So it's to keep on learning, keep getting better. That's the ethos of the Engine Performance Expo. And man, today so far, it's been that. And
what a day, what a day, what a day. Yeah, my brain is swollen. I've learned so much today.
They told us, don't start cars. We are not going to listen.